Wait, hang on. Just give me 1 second. Don't remove that yet. Yeah. No, it's not that. It's usually it has to do with the resolution, and that's not changed. So, does anybody know how to fix this? Otherwise, everybody's going to have to come up to the front or quickly use our So it's going in.
Right now we're limited day by 6, I guess.
Oh, they have HDMI. How long HDMI?
Well,
oh no, that's HDMI out. I don't know where it's going.
so
Yeah. Yeah.
well, also it's trimmed when he presents his slides. Yeah, I think so. Because if you present like I thought it was going to be small. Oh, did it look small? Okay.
Mirror. I tried that.
They used to underscan. No, doesn't help.
That didn't do very much.
Did that?
I mean, it changes the resolution, but it doesn't change the size of the display.
Actually, that is.
No, it's. I mean, I don't think it's big.
No,
Is it?
I think you're right. I mean, why don't you? I'll take a look at the projector.
I mean, that was high resolution.
Should probably close some of these windows just to be safe. I don't want to have them projected like everywhere.
Yeah, well, you're not. Sorry.
I might just need to physically move it back, but
Yeah.
you can bring there's nothing on the screen at all right now.
It's coming back up now.
I'd leave it like that and just do %.
Yeah, I mean, at this point, it's 303, so.
%.
It's showing up completely. Good enough. Oh, good. Thank you.
She is. It's her birthday today.
All right. Let's get started. My name is Jana Iyengar, and if everybody could find a seat quickly, we are already late, which is not a very good thing, given that I have like 75 slides. I don't, I'm kidding. So this is a quick tutorial, and basically to give you an overview of what's going on in Quick, and if you've heard of Quick, and so on. I'll just start. So here's what you can expect over the next hour. A brief history of Quick, what the motivations were, what drove us to actually build Quick and work on standardizing something like Quick. A high-level overview of the work that's going on in the working group, where the working group is today, and you should find this tutorial useful if HTTP2 and QUIC are buzzwords. You've heard them, you've seen them, but you don't know what they are. If you can break BGP, but you think of TCP/PS, that's for fluffy people. If you can write an app in 15 minutes, a mobile app, I couldn't do it to save my life. But you've never seen a TCP dump trace, then this presentation is for you. Just bear in mind, to the other people who already know what QUIC is, this is not a working group meeting. Please don't turn it into one. If you're already participating in QUIC work, please feel free to offer clarifications at any point in time. And this holds true for everybody in general. Feel free to interrupt me, but if I need to go on to the end of the presentation, I will say so. There are no questions for people who are already participating in QUIC work. Sorry, save your questions for the working group meeting. And you'd probably rather be staring at your laptop screen anyways. So with that, let's get going. So what's QUIC? A very brief history of QUIC, because you might have heard of QUIC as this thing from Google, as this thing that's a working group, and you're completely confused exactly what it is. It was an experimental protocol. It's been deployed by Google, and it started in 2014, the deployment of QUIC. This has been quite widely deployed between Google services and Chrome and other mobile applications such as YouTube app and Google search app and so on. This basically was deployed widely because it improved page load latency for us, it improved search latency for us, and it improved video rebuffer rate, among other things, for YouTube. So there were a lot of benefits that we saw from having this experimental protocol, so we deployed it widely, and it's what we would consider a successful experiment today, to the extent that we've deployed it to, it's about 35% of Google's egress traffic is QUIC, which by Sandvine's estimates is about 7% of all internet traffic. Akamai's deployment started in 2016. Akamai has deployed QUIC and is offering it as a thing that their customers can opt in, can choose to use. The working group for QUIC was formed in the IETF in 2016, last October, in the after the Berlin IETF. And the goal of the working group is to modularize and standardize QUIC in parts. QUIC was an experiment. It was built as like one big monolithic thing. You'll understand these things as we go through. I'm just giving you a rough, quick, high-order history of what's happened so far. And the working group's goal is to use HTTP as the initial application for QUIC. Before I move on, just so I know who my audience is here, how many of you are not familiar with what QUIC does? How many of you would consider yourselves newbies to QUIC? Excellent. This talk is for you. The others, I don't care about. So let's start with what HTTP2 is before we actually get into what QUIC is. And actually, before we talk about what HTTP2 is, we need to understand what a web page looks like, because we're going through a brief history of HTTP first before we get to QUIC itself. So what does a web page look like? Well, it looks like this. There's the IETF web page. It has a bunch of objects, scripts, various things that you're familiar with. Lots of things essentially make up a web page. So how does HTTP1 do this? How do you use HTTP1? How does HTTP1 transfer bytes? How does HTTP1 transfer these objects between a client and a server? Well, first, you need connection set up between the client and the server. What do I mean by connection setup? It's a one round trip to set up a TCP connection, and about 2 round trips to set up a TLS. If you're doing 1.2, then a 1.2 connection. And before you rush, yes, we'll talk about TCP fast open and we'll talk about TLS 1.3, but not yet. We'll get there slowly. So it takes a fair amount of time to actually set up an HTTP connection or a TLS over TCP connection before you can even transfer these objects down from the server to the client, request and transfer these objects down. After the setup, HTTP requests and responses flow over this connection that's been set up. Going further, here's what it looks like, roughly. Let's say there are these 3 objects that we saw on the IETF website. And, excuse me. And the web server has these 3 objects. You have a client, that's a browser, and we just went through this 3 round trips of setting up a TLS over TCP connection. And now we are talking to the web server, but we don't have the objects yet. So the client first sends a request over the TCP connection and fetches the first object from the server, then sends a second request and fetches the second object from the server, and then sends a third request and fetches the third object from the server. This is all wonderful. So we have the web page and it shows up and it's great. Can we do better? Any ideas? I'm sure you read something. What could you do to make this better? Come on, tell me the right answer, because we have it. What's it? Let's pipeline them. Excellent idea. As it turns out, that doesn't get deployed very well. What else can we do? Do them in parallel. Excellent. Why didn't we think of that before? Well, as it turns out, we have thought about it before. And that's roughly what we do. How do we do it? The problem here, of course, is that as you're sending objects one after the other, the second object shows up only after the first object is completely transferred. Well, that's not fun. What if you want to see the 5th picture on a page of thumbnails? You have to wait for the first 4 to load, and that's really not fun. So ideally, you want to basically be able to see them roughly in parallel, because a web page has a whole bunch of different objects. And that's what we ended up doing. This was a hack. What was the hack? Well, the client wants to request the first object. So it says, hey, web server, here's a TCP connection, and now please send me the first object over this connection. And the client says, oh, I'm a client. I would like this other object from you over a new TCP connection, and does the same thing for all objects. It doesn't have to do the same thing for all objects. In this example, it does. And it fetches all of them. They come relatively slowly. They come slower than each one of them would have in the first case, but they all show up. Anybody see any problems with this approach? Say that again. Too many sessions. What does that mean? Time. So you need to set up, each one of these connections has to get set up separately. And in the internet, where we know loss is king, it can be a pretty painful affair. What else? Just one more thing. Say it again. What kind? So it's 3 connection establishments. There's another one. There's a socket overhead at the server. The server's running out of sockets much faster, right? Each one of these connections consumes space. There's a third. There's one general thing, which is that you have 3 TCP connections now, which are competing with each other in the network for bandwidth. That makes it also troubling. We'd ideally like to not do this, right? But we didn't have a better way to do this for a very long time. Or maybe we didn't care that much. But we definitely didn't have a better way to do this for quite a long time. This is still better. So this is what a lot of browsers even now do. When you go to an HTTP 1.1 site, and you might see recommendations on various websites that say, if you want to increase your speed, increase the number of connections that you're allowed to use to 200. Bad idea. Don't do that. Better idea? Use HTTP2. What does HTTP2 do? Well, it tries to deal with the same head-of-line blocking problem, but in a different way. So here's what it does. The client wants to send a request for one of these objects, and it creates what we'll call an HTTP2 stream. Not we'll call, that's what the HTTP working group calls. And that's a stream. The idea of a stream will become clear in a moment. Similarly, it wants to request the other 2 objects as well. It requests them over 2 other HTTP streams. All of these streams get mapped to the same connection, meaning that the browser here, or the HTTP2 part of the browser, is multiplexing pieces of a request and a response over the same connection. So the server sends them out, And we get them, again, slightly slower than if you would have gotten any one of them, but you get them in parallel. And they go over one TCP connection, thereby avoiding a lot of the overhead that we talked about in the previous case. This is all fine and dandy. This is awesome, right? Can we do better? Anybody? Hello? Am I the only one here? Apparently so. Don't set up the connection in the first place. Yes, well, you won't get the website, you won't get the web page. That'll be a bit of a problem if you're actually trying to get the web page. Come on, I'm not moving forward until I get an answer from this crowd. SCTP, somebody said SCTP. Yes, it would actually make this better. I don't know who said SCTP, but you may not want to identify yourself. It will make things better, indeed. Why does it make things better? Why does SCTP make things better? A session layer, but what does it do? It's not a session layer, it's a transport protocol. Come on. Congestion control, Mike, go on. Congestion control knows about the streams, yes. The transport knows about the streams. The transport knows that there are 3 different objects going over this connection. With TCP, that's the problem. In this case, you still have head-of-line blocking. Where does the head-of-line blocking show up? Well, this gray line that you see up here, that's basically a byte stream. So all the multiplexing happened above TCP, in TCP, because I don't know what you're sending me. It's just a bunch of bytes. And TCP will make sure to get them all delivered to the other side in perfect order. But we want parallelism. We don't want perfect order across all of these objects. TCP doesn't know that there are many objects going over, it's going through this connection. SCTP does. But we are not here to talk about SCTP. We can have that fight later. That is, I do actually have a slide about something like that later. So, but the idea is exactly the same. The problem here is that the transport does not know about streams, does not know about parallelism, doesn't do anything to give you parallelism. So, how does HTTP over QUIC work? QUIC solves all of your problems. We can shut down the IETF after this. So, how do we set up connections in QUIC? Well, it's quick, haha. 0 round trips to a known server. If you're talking to a server that you've already talked to, if a client is connecting to a server that has spoken with in the past, it takes exactly 0 round trips to set up a connection. That's like magic. How can you set up a connection in 0 round trips? Well, you can't. You send a connection handshake packet and you can immediately send data after it. What it means is that you don't have to wait for the server to respond to you. You can expect that the server will finish its handshake as soon as it receives this packet from the client. And if it doesn't, then you still have a 1 round trip fallback where if your crypto keys are not new, then you have to go through a little bit of work. I'm not going to go into the details of these things, by the way, into the details of how the handshake itself works, because that would take me a while longer, and I'm not going to do that here. And by the way, if you want to know about that, ask for a TLS 1.3 tutorial, please. If version negotiation is needed, then we take up to 2 round trips. But these are the uncommon cases. And the most common case is expected to be the 0 round trip case, because when you go to a website, when you go to a server and request a resource, it's very likely that you're going to go back to the same server and request another resource. This is just simply locality, and that's very common. And yet, I haven't yet forgotten about TFO and TLS 1.3. We'll talk about that in a bit. After setup, HTTP requests and responses flow over a quick connection. So a quick connection happens much faster than TLS 1.2 over plain old TCP. And that's one of the big benefits of QUIC. So how does this look in practice? This is what you expect to see. You have a quick connection between the 2 endpoints, and there are objects at the web server. Again, the client request makes a request over one HTTP2 stream, which now maps to two quick streams. The details of this, I will not go into why, but Mike is in the back. So find him after this if you want to know why. Mike, raise your hand. There you go. That's Mike Bishop. He's the editor of the HTTP mapping draft, and he's the reason the world looks like this. So you can blame him for it. So we have two quick streams that are used per HTTP stream. In short, one of the streams is used for headers, the other stream is used for body, which is fantastic. So that's an HTTP2 stream, that's a quick stream. And that's what happens with quicks. This is what happens here. Similarly, the client sends requests for other objects, and they end up on other quick streams. What is a quick stream? Maybe you understand now roughly what an HTTP stream is. Like I told you, an HTTP2 stream is where HTTP2 multiplexes things above into the things below. In this case, it's slightly different. HTTP2 knows about quick streams below, so it takes the request from above, the response from above, and ships it through multiple streams below. So what does quick do? Well, it takes those and multiplexes them over the connection that it has to the other side. So this is what you have. You have a multiplexed transport. Quick is a multiplexed transport. It multiplexes multiple streams over a single transport connection, which means one connection setup. It means one loss recovery context. It means one congestion control context. It means Quick can do priorities if you wanted to do priorities across multiple objects. So it's very exciting. It's a lot of interesting things that we can do. And at the IETF, we love doing more things. So there we go. That's what Quick does. And again, the objects are received in this manner. So going back just a bit, I told you that there was an experiment at Google, and then there's IETF Quick. So I want to clarify exactly what the difference is. There was an experiment. There still is an experiment. It's deployed. And this is what it looks like. So Google did an experiment, built a protocol, and we called it Quick. And this is what it roughly looked like. It basically maps to the standard HTTPS stack in this manner. But it runs over UDP. As you can see here, the protocol was built to run over UDP. I'll talk about that later in the presentation. And HTTP maps onto Quick. We had our own mapping that was fairly simplistic, and it's getting much more sophisticated now as we are going through IETF working group work. And we used our own homegrown, our own little proprietary Quick crypto for doing the handshake, for doing the rapid zero RTT connection setup. So this was an encrypted transport in the experiment, and we like it as an encrypted transport, but it used a proprietary handshake mechanism. Since then, we've had TLS 1.3, but I'll get that in a moment. So what's a Quick working group doing? Like I said, here's what old Google Quick looked like. Of course, crypto was proprietary, so we want to get rid of that, and we want to do a whole bunch of other things at the IETF with it. But first, we didn't want Quick crypto, we decided not to have Quick crypto in here, and just leaving it like that would make it an unencrypted transport, and it would make a lot of people very, very grumpy. So we decided to use TLS 1.3. which was developed after Quick Crypto, but it gives you the same benefits as Quick Crypto, meaning it gives you zero RTT handshake latency. This is the brand new hotness in TLS, by the way. So if you want zero RTT handshakes, use TLS 1.3. And the reason that it's embedded inside Quick is because we are actually doing some careful work. And you, again, remember, we want parallelism. TLS usually sits on top of TCP, which means it's used to a stream of bytes underneath it, and it offers roughly that above it. So you have to do some work to make sure that TLS framing, falls within Quick packet boundaries, and that when one packet is lost, that other stream data can still be decrypted and delivered. So TLS 1.3 here is really not sitting under Quick. It's actually being integrated with Quick. It's sitting around Quick. Oh, sorry, Quick is sitting around it, meaning that the TLS handshake actually happens inside of a Quick stream. So we are still carrying TLS handshake instead of quick packets. So the working group is doing a ton of work, and I'll talk about that later in the presentation. The goal for us is to have that. That's the first goal. The first goal is to have an HTTP mapping on top of QUIC and make it work with TLS 1.3. Going forward, the idea is that once we have finished this, we'll have a protocol that's modularized enough that we could, with relatively little friction, replace the handshake from TLS 1.3 to a new one, say TLS 1.4, or God forbid, TLS 2.0, because that's never happening. And you could replace, HTTP with like WebRTC and so on. That's the goal of the working group itself. Once you finished the work, this is what we expect the output to be. Maybe some of this sounds familiar, and I've mentioned some of it. I mentioned some ideas that you might know, like SCTP, like multi-streaming, like other things. Yes, we are just replaying some of the greatest hits that we've already seen. The difference is that we are trying to make it deployable, and we're trying to integrate it with the needs of today. So yes, the ideas you see come back. This, by the way, is not limited to QUIC. It's all of computer science. We love to replay ideas, and we're doing exactly that. But we're adding something new, hopefully. We're adding a bunch of new features and a bunch of new things which have never been done before. Zero RTT, for example, with the crypto handshake has never been done before. So we feel like you're always on thin ice when you're doing that. So there's a lot of new exciting things as well. So some of the work that is quite relevant and very related to what you've seen so far. Of course, like I said, TLS 1.3 is being used in ongoing QUIC. So it was a QUIC crypto used to be the thing that had zero RTT, but now we have TLS 1.3, and that's what we're planning to use. TCP fast open, or if you go further back, if you used to work on those green things called terminals, you might remember TTCP. How many people here actually remember TTCP? All right, excellent. So TCP fast open was recycled from TTCP, and of course we will keep using the same ideas. These are very happy to steal ideas. TCP fast open allows you to get TCP connection set up in zero RTT. So you might ask, well, if you have TCP fast open and you have TLS 1.3, can't you get connection set up in zero RTT with TCP and TLS? And yes, you can. The problem, again, is in deployability. TCP fast open is still, after 7 years, trying to get deployed. And it's a hard problem because you need to change client-side operating systems for changing TCP, and you need to change middle boxes, or at least make sure that middle boxes work with this modification in TCP. And it's also limited to one packet on the client-to-server direction. And other ideas like TCP session, which predates SCTP, which predates SST, all of these talk about multi-streaming as a brand new idea. It never was a brand new idea. Parallelism has been there. Parallelism is an idea that's as old as the hills. And there are a bunch of shared ideas with all of these old protocols, and we are very happy to steal all of those ideas. And if you have more ideas, we're happy to steal them as well. There are some subtle differences from these protocols. I'm not going to go into them here, but I'm happy to answer them during the Q&A session. So here are the broad design aspirations that QUIC has. Deployability is critical. We want QUIC to work on today's internet, not on some future IPv6 internet. It has to work on the IPv4 internet, which is riddled with middle boxes and everything else. It has to work on currently deployed client operating systems. If it doesn't, then nobody's going to implement it. And that's something that we've seen in the past. With SCTP, we had a lot. I worked on SCTP for 6 years. So there was a lot of work in just trying to convince folks, Microsoft, to deploy SCTP. This was work. And you have to answer, well, can you deploy this today? And the answer is, well, no, because middle boxes won't allow SCTP through. And then the answer is, then why should we implement it if it doesn't work? Until you implement it, middle boxes won't change themselves. So you have this vicious cycle of, just not going anywhere. So that is important. We want to be deployable on today's internet, which is why we have UDP, but I'll talk about that in a moment. And we want to be able to evolve, because today's internet is obviously not going to be tomorrow's internet, and we might have different needs, we might have different applications. We want the transport protocol to adapt, to evolve. We might want to call this I had an idea about calling it the transport protocol, because once you have versioning, once you have evolvability in here, then every new transport looks like a new version of this old transport. So you could think of it this way. Low latency connection establishment was critical, because again, web pages are very latency sensitive. As an application, the web itself has gotten very latency sensitive over the past decade or so. So it's really important to have low latency connection establishment. Multi-streaming, we've talked about that. In addition, we wanted to have better loss recovery and more flexible congestion control. So TCP loss recovery has been for a long time just riddled with complexity because of some early design components that were in TCP, and you can overcome them, but it takes a while to get there. We had the opportunity to design this from scratch, and so we have loss recovery that is just fundamentally has more signaling and ought to do better under a larger set of scenarios. And we want to be able to have flexible congestion control. UDP also has, does everybody here know what the NAT rebinding issue is? I'll very briefly summarize it. For TCP connections, it's easy to see that when a TCP connection goes through a NAT, the NAT has to maintain a binding for the connection that's coming into the NAT and leaving the NAT. For TCP connections, you usually receive a FIN or something like that, or a reset packet that tells the NAT, oh, this connection's gone, so you can discard state for this connection. If state is discarded for the connection before that happens, the TCP connection will stop working after that point. The same problem exists for QUIC, except NATs have no idea that this is QUIC. They just see it as UDP. They are not expecting a FIN bit or a reset bit to be received. So today's internet, in general, has a shorter UDP timeout in NATs than for TCP. So we needed to have some resilience to NAT rebinding, which is that when you mid-connection, a packet might end up getting bound to a new port, which will arrive at the server as a completely different 4 tuple. And the server has to deal with it and know that this belongs to the same connection. So QUIC uses an explicit connection identifier that's in the packet, and that the server uses to collate packets that belong to the same connection, irrespective of 4 tuple. Multipath is something that's on our radar. It's in the charter for the working group to work on, but it's going to happen later once we've resolved some of the more burning issues that we need to do. So just on a couple of these points, I'll go into just a little bit more detail. Deployability and evolvability. How do we satisfy this constraint or this design aspiration? The first thing that QUIC does is we will use UDP as a substrate. Everything I'm talking about, by the way, here is QUIC as we are working on it in the working group. As I mentioned to you, the working group uses things that the experiment informed, but the working group is moving much further with it. This enables deployment through middle boxes, and it allows us to do user space implementations, meaning that we do not have to wait for client operating systems to get upgraded, and that happens at a very slow clip. Version negotiation allows evolvability. None of the transports that we've seen so far have versioning in them. This is an odd thing, because almost everything else does have versioning in it, but transports don't. So version negotiation allows us to evolve the wire format of the protocol going forward. And to make sure that middle boxes don't ossify the bits that we are sending on the wire today, allow us to change our wire format going into the future, we encrypt most of the QUIC packet, and we authenticate all the headers are fully authenticated, and some of them are visible, but others are not, so that middle boxes can't tamper them. The whole packet is tamper resistant. This is again to help us retain QUIC's evolvability going into the future. But it also befuddles network operators, because network operators are used to. Any network operators in the room? Would you like to identify yourself? There you go. Yeah. No, I'm not asking you. Yes, thank you. This is a problem for network operators because they're used to seeing TCP. They're used to seeing all the bits that are on the TCP header, and QUIC says, well, we're not going to show you anything. Right? This is only for the endpoints to see, and that's a real problem. So we need to now sit down and do the hard job of identifying which bits are necessary, which bits have become used over time simply because they were visible at the time and are for just craft. And that's a hard conversation to have because it's hard to find the core of what's necessary, and it's hard to determine how much whatever we expose, that in mind, to the network, we'll have to assume gets ossified going into the future. So we sort of have to figure out how to enable ossification in a way that allows QUIC to evolve while getting ossified in some pieces. Yeah, question.
So you're saying that this is a work that yet needs to happen?
That's correct. It's happening.
None of these headers are currently exposed.
There are some headers that are exposed in the current Google deployment. That's going to change completely because that's an experimental protocol anyways. I'll talk about actually exactly what's going to change in the header. But yeah, this is an ongoing conversation.
So today, for example, someone wanted to add an IETF based on 1990, that's not.
Well, it's possible for the current QUIC. The current QUIC is not your future QUIC. The most important thing is that it has to be done in a manner that's sensible to do. The versions that we use right now, the QUIC version that you see on the wire is going to be different from the QUIC versions you see in the future. And as I said, the packet header format is also changing dramatically. So the connection ID won't be in the same place, for instance. Like I said, I'll talk about the header actually in a little bit of detail after this. But yeah, this is ongoing work. This is why the IETF working group is so critical for sort of the long-term success of this protocol. So exactly that question, I'm going to show you very briefly what a QUIC packet used to look like, or what it looks like in pre-consensus world. Right now we have a proposed header change. We still don't have consensus on that, but I'm going to show you both of those to give you a sense for what this actually looks like on the wire. So QUIC has what we call regular packets. These are the common packets that you see, the data carrying packets. And they have flags, they have a connection ID that you use for identifying a connection. It's optional, by the way, because if either endpoint can negotiate and say, well, you don't need to send me a connection ID because your 4 tuple is enough for me. Which is common, by the way, in the server to client direction, right? Because the server to client direction, you're always receiving packets on the port that you're sending requests from. Version number is optional in here, but it's present in this format. And there's a packet number, which is synonymous with the sequence number in TCP, but different. And I'll talk about the difference in a bit. And then there's the encrypted payload. This is QUIC frames. This is the entire payload of QUIC. When I say the payload, this is not just user payload. This is QUIC frame headers as well. So what are QUIC frames? Well, this is all the signaling, a lot of the signaling that QUIC does to its peer, the QUIC endpoints do with each other, happens via frames. So you have ACK frames instead of ACK packets or an ACK bit in the header. We have an ACK frame that can give you a lot more detail about what all is being acknowledged, how long it's been since those packets were received, and so on. Then you can do flow control in here, which is the window update frame, and the stream frame, which actually carries user payload. As we saw earlier, QUIC carries user data in streams. This is exactly where it shows up on the wire. Now, all of this is encrypted, right? So nobody else can see this, but for the endpoints at the moment. The stuff in the orange can be seen, but not tampered on the network. These are regular packets, however. There are other packets which are unencrypted. There's version negotiation because, well, we don't even know the version we are speaking yet. Obviously, we can't have a shared key yet. So version negotiation looks something like that. And there's a public reset packet, which is in the, like I said, in version 01 of the draft specifically, is an unencrypted packet. So this is a packet that you can send to reset a connection. There are a number of problems with these header formats. Part of it is that there are a number of packet types. that are going on here, and it's hard to figure out exactly what a quick packet looks like from the plethora of options that you have in the space. So there's a proposed change to the headers, to the packet itself, that allows us to somehow try to sort of streamline this. So there's long header packets which start with the bit 1, and then there's a packet type in there which tells you what type of packet it is. It could be a version negotiation packet, it could be a public reset packet, it could be or a regular 0 RTD packet, a handshake packet. It's always has a 64-bit connection ID. It has a 32-bit packet number, a 32-bit version number, and it has a payload, which is type dependent and may or may not be encrypted depending upon exactly what type of packet it is. For example, a version negotiation packet is not encrypted. Again, for the same reason, we haven't quite negotiated a key yet. But there are other payloads that we want encrypted. We want other things like a public reset to actually be encrypted or actually have a proof of some sort from the peer. And that's going to show up here. The type of proof itself, it's TBD. But all of this is work that's ongoing. As I'm saying, this is proposed. We are going to actually have a consensus call on this in the working group this week. For the common case, where you have a lot of data that's going back and forth, once you've established the key, once you've finished the handshake and everything else, there are the short header packets. I'm not going to go over the details, but basically it's a shorter, tighter version of the packet header. In the best case, you can have this be exactly 2 bytes, which is quite nice. A packet header of 2 bytes, that's awesome. Or 3 bytes in the common case. That's what we expect to see. And this will always have an encrypted payload. So these are proposed. I'm not going to go over, a lot more detail because this might change as we go forward. But I wanted to show you what the packet looks like and the type of work that's going on in the depth of the work that's going on in the working group. On congestion control and loss recovery, I mentioned earlier that we are trying to make this better in QUIC. We incorporate TCP best practices. And because we can design this from scratch, we've decided to use new packet numbers for retransmissions than for original transmissions. How many of you are familiar with the retransmission ambiguity problem in TCP? Fair number of you. The others, please ask your neighbors. But the problem in TCP is that a sender, when it receives an acknowledgement for a packet, which it has retransmitted in the past, let's say a sender sends packet number 10, later on retransmits it, it sends it again as packet number 10 or with sequence number 10. When it receives an ACK for 10, it doesn't know which of the 2 packets it is for. We've worked on this for a long time, and we've tried to. There are a number of proposals that make retransmission ambiguity go away, but it's a problem that came because we did not have different packet numbers for these different packets. QUIC allows you to do this. Not allows you to. QUIC requires you to do this. And by the way, the packet number is also used for crypto. So there's a lot of sort of integration of functionality between the crypto and the transport, and it's not separated as well, which allows for lots of efficiencies to come out of this. QUIC also has a more verbose ACK, and it specifically lays out packet receive times, allowing a sender that receives an ACK for a packet to do more precise RTD computations. So what's the working group up to? As I pointed out one example of what we were doing in the working group. But broadly, it's really taking an experimental protocol and turning it into like a professional one. It's making it capable of handling all the corner cases that nobody had thought about before. It's a makeover. It's quite a deep number of changes that are happening to the protocol. So the working group is figuring out how to map HTTP cleanly to QUIC, how to use TLS 1.3 with QUIC. Number of open questions that are unresolved yet. Like I said, public reset proof. We still don't have resolution on that. And how to make QUIC work for non-HTTP applications. That's not work that we are doing immediately, but that's certainly something that we all have in the back of our minds as we make design decisions in the working group. So is this just Google's QUIC? No, it's not. I want to be very clear that Google's QUIC was the experimental protocol, and the QUIC working group used the experiment as a starting point. All the work that's going on is fairly fundamental to how QUIC works and how we think of QUIC. And the current IETF spec is already, it's at 0.02 right now, but it's already miles away from where we started 5 months ago. So it's a fantastic example, by the way. The whole process was a fantastic example of running code and forming protocol design. We started off with a protocol, an experimental one that was done by Google, and all the results drove drove a lot of the design decisions that have happened in the IETF world. And anything that we do now in the IETF, if you have questions about something that we don't know which one's going to do well, we can immediately take it, backport it to Google's QUIC, and see how the performance, which one is more performant. That allows us to make decisions going forward as well. So the goal is for everybody to use the version of QUIC that comes out as standardized with the IETF. There are 2 QUIC implementations at the moment. Neither of them speak the IETF version of QUIC yet. These both speak Google's versions of QUIC. They're available. And there are debugging tools. The most important one I'll say is Chrome net internals. So if you have a chance, go to chrome://net-internals, and you will see QUIC as one of the items there. And you can click on it, and you can see all the QUIC sessions that you have established to various servers that speak QUIC. So if you're speaking to Akamai, you might see QUIC. If you're speaking to Google, you will see QUIC. And that's, I think, it. How are we doing on time?
Yeah, 14 minutes for questions, which
14 minutes for questions.
14.
Awesome. Yes. Ha 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 ha. No, you said quick questions, so I have to do that. Sorry, go on. I didn't. Yeah, no, that's great. Keep running with the theme, yes.
You mentioned that this was successful experiment. Can you share some numbers that made it successful?
I can. What number can we share? That's a high order.
I mean, we can. Actually, I mean, I might actually refer you to the Barboff presentation from.
Yeah. So if you want to look up the presentation, we had a number of detailed numbers in the presentations from the Barboff in 2015 summer in Prague. We had a quick Barboff.
The Berlin ones.
The Berlin
ones also include things like UDP reachability.
That's true.
Percent of users ended up using.
Yes.
QUIC.
So there are numbers from the BOF in Berlin last year that should show you some. I can give you some numbers. Again, these are not universally. These are our numbers, right? So the numbers will be different for others, which is partly why we want to see other people deploy QUIC and see how well it works. But we saw rebuffer rates for video playback reduce by about 20% by 20%. By 20% and greater than 20%, but yeah. And this was, we saw this, the benefit was more. This is actually important, so I'll just take a moment before I take your question. The benefit was higher, the worse the network was. So when you looked at benefits in, say, India, for example, or Brazil, where the networks are crappy, we saw more benefits with QUIC. The difference between QUIC and TCP was higher than in the US, for example, which again tells you that QUIC is not, it's not icing on the cake. It's actually fundamentally changing, and it's making HTTP work well for crappy networks.
Giovanni, this is working, yeah. Giovanni is at the end. Great work. I have a question regards Anycast, IP Anycast. You got stuff probably on CDNs as well. So can you tell me, I think that was another concern in the design, right?
Can you speak closer to the mic?
Yeah, so my question is, QUIC is also designed to operate with Anycast networks, right? So can you talk a little bit about that?
There's not very much that you need to do special to operate in an Anycast network. As long as you're getting routed to the same server, you're okay.
All right, okay.
Right? I mean, the IP address points you to a server. If the client moves, changes IP addresses or so on, and ends up going to a different server because of it, yeah, that's an issue.
Okay. And what about DDoS attacks, like amplification attacks? Is this resistant to that? Like, can be exploited for amplification?
Well, we tried really hard not to allow for that to happen. In general, there are rules around how many packets can be sent. In the first round trip, for example, you would have the same. I think you have I don't think you have any new DDoS implications for using Quick, as far as I can tell.
Okay, cool.
I'll look to some other people in the room to verify that that's the case.
Thanks.
But yes, I believe that's the case.
Hi, Robbie Simpson. Great tutorial. Since you're building a new transport protocol, why build it on UDP at all? Why not just start from the ground floor?
You said great tutorial. Why don't we stick with that theme? Let's talk more about how awesome this was. Because of what I said, deployability. You can't deploy anything that's not UDP or TCP on the internet today.
Okay.
We've tried this with SCTP and we failed. And we certainly did not want to wait for another 10 years before this got out there. There could be a day in the future when we can actually make this natively available over IP. And it would be trivial to take Quick and dump it on top of IP directly at that point.
Cool, thanks.
All right, thank you. Can I ask a question of slide number 11?
Boy.
Is maybe
I'll get there. Go ahead and ask.
Yeah, so, just maybe a very basic question. You said about that, you want to stream everything on the Quick with one request, right? How did the client at the first level know how many objects are there in the
It's not one request. It's multiple requests.
Okay.
Each request goes over a stream.
Right.
All requests go over their own stream, but they all go over the same connection.
Okay.
So the client can send a request as it does always. Whenever it has a request, it sends it. The request that it sends end up becoming a stream, or a couple of streams in this case, inside of the same Quick connection.
Okay. No, I'm just trying to understand that 3 objects are there, right?
That's right.
So if client didn't connect to the server in the first place, he had no idea that how many objects are there.
Sure. So the client does connect to the server and sends a request first. Let's say get slash.
He discovers that first.
Well, you have to ask. You always send an HTTP request first to the server, right? So when you have a TCP connection, what happens? You set up a TCP connection, and then the client sends a GET request. And that goes out, and you get a response back. You look at the embedded links, the embedded request objects, and you ask for all of them. Same thing.
Okay.
Except each one of those requests is going over a stream over inside of Quick.
Hi, I'm going to ask 2 questions. One, hopefully, with a quick answer, and then a second one.
Sure.
What was wrong with SCTP over UDP?
A few things.
Okay.
The first thing is that again the handshake is a completely different beast. The second thing is that it wasn't optimized for web transactions, and from our point, and the third and the most important thing is that it wasn't integrated with the security protocol. The only way you could do that would be sort of like taking SCTP, taking DTLS or TLS, and figuring out how to smush them together. And now trying to write code or trying to take pieces of software and making them work like that is hell. So this is basically designed from the ground up that has very clear requirements instead of trying to retrofit something.
Okay.
And we thought it was worth doing that.
Second question. Have you, I know you're probably going to say this is out of scope for the current work of the working group, but one of the things I liked out of SCTP and was kind of trying to look to reuse myself was the partial reliability functionality. Yes. Is that on your roadmap, or is in that the back of people's minds? Or?
It is in the back of people's minds. Okay, but that's cool. Exactly where it is at the moment. Yeah. It's definitely something that we'll want to address when we go past HTTP.
Yeah.
At the moment, again, the goal is to try to build something that works for HTTP, and then once you've done that, when you get to like video or WebRTC. But yes, that's absolutely on everybody's mind, and we would want to get there at some point.
So this is not actually a question, it's a favor request of all of you all. So I'm part of the edu team that's responsible for these, and there's a survey associated with this, and the link to the survey didn't make it in here. This was a fabulous tutorial, but it would help us with planning purposes for people to respond to the survey, and I'll get the link sent out, and also to send in suggestions about future topics that you would want. I think we had a really good one on DNS privacy last time, and this one has been superb. So thank you.
Thank you, Karen. And there's also a question of if you want to do like a more in-depth one on Quick, sort of go into the innards a bit more.
Right. This was actually one of the conversation points we had was, should this be a 1-hour tutorial or a 2-hour tutorial? Should it have 2 parts? These are all the kinds of things that you could actually give us feedback on a survey.
Yeah, if you'd like more depth in another tutorial next time, then ask for it.
Hi, if you use TCP, you're losing the path MTU discovery mechanism, right? Is there any mechanism on UDP you guys have to discover the path MTU?
Yeah, no. I mean, no, we don't have any mechanism at the moment. We did work on sort of measuring what MTUs work best.
Okay.
And we have a chart somewhere, which I'm happy to present. I've been looking for a venue to present some of the experiments that we ran, the data of, some of them are present in the BOF slides, but this one isn't. But yeah, we chose a fixed size based on what we saw worked.
What did you fix? What are the size you?
13, what is the UDP MTU size?
1350 for V4, it ends up being right around 1408 bytes, or
yeah,
it's just around 1400 bytes with the IP header.
Yeah.
Still, the performance is better than 1500 TCP.
Say that again?
Performance is still better than the normal TCP.
Yeah, I mean, we have it deployed, and performance is still better now. Okay. I mean, the reason is because, again, the point is that one of the short things is to bear in mind is that the experiment, as I told you, that we have deployed in Chrome for Google services, tries to use QUIC and races it against TCP. So if you're using a very large MTU, the first packet is padded to be maximum packet size,
okay,
and it doesn't get through the network, gets dropped, and Chrome quietly falls over to TCP and uses that. So we're sort of using the best of both worlds.
One addition is that, at least based on our anecdotal experience, once you're in the 1400 to 1500 byte range, the network is no longer limited by the number of packets it can send, but actually by the number of bytes in the packets. So except for some minor extra like IP and et cetera, percentage-wise overhead, the cost of sending like a 1400 byte packet versus a 1500 byte is incredibly small, relatively speaking. And at least at Google, we'd actually, I think, downsize the packets to some slightly smaller number anyway, because fragmentation ends up being more of a hassle than it's worth even for TCP.
Yeah, yeah, that's right. I had missed the fact that you could pack a few more bits, but it doesn't matter that much.
Thank you.
Sure thing.
One of the design aspirations that was mentioned was about NAT rebinding. So how is it covered? How is it taken care of?
Taken care of? So NAT rebinding affects endpoints that look at the IP and port to determine, to identify connection. You look at the 4 tuple. In QUIC, you would use the connection ID, which is in the QUIC header. Even if the 4 tuple changes, you can use the connection ID to identify the connection. Okay. That's how it works. That's it. I'm sure we have time left. Demo. Do you have time to do a demo?
You want to pull up the internals?
You do that?
Yeah, sure, we can do that. You want me to pull up the internals?
Yeah, go for it. I can point to things from here. So if you go to Chrome://net internals, you'll see on the left side, QUIC and HTTP2.2. But there it is. Those are 3 QUIC connections that are using QUIC version 35. And this is Google's QUIC version 35, Q035 specifically. And if it shows a bunch of things there.
How many sent and received, how many lost. This is lost from your perspective. And then you can go to a connection ID. Is it, oh, sorry, I realized you can't see me. Okay. Yeah. So I can look at all the sessions that John's computer has been doing to Google since I started doing this. Actually, let me go to like youtube.com. That opens like 1 billion connections. There we go.
Oh yeah. You can see my email.
Yeah. So you can see the full handshake with the cert. You can see how long everything takes. You can see every single packet that's going by. Probably one of the more interesting things is that you can see the handshake process. So this is the crypto reject with all the fields that are available in it. Like this is an indication that we're offering ASGCM and CHA-20 as ciphers. I guess we're checking CT compliance. You get an idea of what's in the acknowledgement frame, the stop waiting frame, which is actually going away. So basically this breaks down every single frame that's inside every single packet as it's being sent or received.
So it's like a very detailed Wireshark trace.
Yeah.
But at the client. And the reason you can do this on the other client is, again, it's encrypted, people.
But it does not actually expose any payload information. So This does not
Oh, that's
give
true.
me.
The net internals won't show you payload information, but even the frame headers, such as the ACK frame and so on and so forth, are all encrypted. You couldn't see them without having the decryption key for the
My
transport.
point is just going to be from a PII perspective. It does show the entire URL, but it does not show any of your cookies or any of the payload going back and forth. And so if you were going to use this for debugging purposes, it definitely has a much lower sensitivity than like a full unencrypted TCP dump.
Yeah, and that's actually really important because we get reports about Quick not working well in some situations all the time. Not all the time. I'm sorry, I shouldn't say that. We get it like once in 6 months. It's infrequent. But when we do get it, we ask people to send us net internals because you can store this and send it off. And this does not have any PII in it at all. So you can, if you are debugging a client, if you're debugging a client's connection, you can immediately look at this or ask them to ship you this, and you can look at the details of what's happening in the connection, or you can ship it to us.
Oh.
So that's all, folks. Thank you so much for, I don't know, staring at your laptops.
Let me check up. Okay.
I want to check. Oh yeah, are you editing? Yes.